The goal of this problem is to find the area of the inner loop of the polar curve r equals 1 minus 2 cosine theta. The graph is already provided, so we can see that the area we're after is this little loop right here. It's almost a circle. We can kind of estimate that this is kind of a circle with a radius of 1/2. So we would expect that the answer might be somewhere around 1/4 pi. It won't be exactly that probably, but we know that 1/4 pi is the area of a circle whose radius is 1/2, so that will be a nice ballpark comparison to take a look at. So keeping that in the back of our mind, how in the world are we going to find the area of this curve, of this shape? So always ask the question, how is this shape created? So for example, where does it, quote, start when theta equals 0? If theta equals 0, we're taking 1 minus 2 cosine 0. In other words, 1 minus 2, which is -1. So when theta equals 0, our r value is -1. So that's actually right here. Okay? And when theta increases, we go always in a counterclockwise direction. So theta is increasing as we go this way around the curve. And then we hit the pole. So the next big question is, let's move this over to here so it is next to the point it represents. The next big question is, what is the theta value when we first get to the pole? Okay, so theta equals what? Well, that's when r equals 0. So set r equal to 0 and solve for theta. And we'll get cosine of theta equals 1/2. And the first theta value bigger than 0 that gives us a solution here is pi over 3. Cosine of pi over 3 is the quadrant 1 angle whose cosine is 1/2. So pi over 3 is going to be the value we use to trace out the bottom half of the shape that we're looking for. So if we integrate from 0 to pi over 3, that's going to give us this area right here. So when we do that, we'll do 1/2 the integral from 0 to pi over 3 of r squared d theta. That's the area of the region I have shaded. Now again, that's half of the region we're interested in. So we also want this, but that's the same shape, congruent shape rather. So we're going to do 2 of these. So just like in the pedal example, we're going to set it up with an area for half of the area we're interested in, and then we double it. That tends to be an easier way because when we take 2 times 1/2, it cancels out, and it's just a little bit cleaner. We certainly could have worked backwards and figured out the theta value before 0 that starts at the pole, so we trace out the top half of the inner loop, and we would probably not have too much trouble figuring out that that's negative pi over 3. So we could forget about this blue 2 here and change the 0 to a negative pi over 3. But that makes things harder because we now have a 1/2 out front, which is not a big deal, but we don't have a 0. I really like having zeros in my bounds of integration if I can. That makes things a whole lot nicer. So this is probably the easiest way to set this up. Definitely not the only way. So we'll integrate from 0 to pi over 3. The 2 and the 1/2 are gone. We'll square the binomial, so we'll get 1 minus 4 cosine of theta plus 4 cosine squared of theta, d theta. I like to simplify this, get everything ready to integrate before I integrate any of it. So I'll use that power reducing identity. And the power reducing identity is going to be the fraction 1 minus cosine of 2 theta over 2. That's being multiplied by 4 because of our coefficient, so that gets rid of the fraction. So we have 1 plus 2 is 3 minus 4 cosine of theta plus 2 cosine of 2 theta. So each one of those terms is fairly straightforward to integrate. So we will get a 3 theta. We'll get a minus 4 sine of theta. And we'll get a plus sine of 2 theta. I'm not forgetting this 2. This 2 got divided out by this 2 because we unchain ruled it. So that is our antiderivative. We evaluate our antiderivative at pi over 3 and also at 0. Woo! And we do 3 times pi over 3 minus 4 times the sine of pi over 3 plus sine of 2 pi over 3 minus 3 times 0 minus 4 times the sine of 0 plus the sine of 0. And this is all going to be 0. So we just have this first term, which is going to be 3 times pi over 3 is pi. Sine of pi over 3 is root 3 over 2. So it's going to be minus 2 root 3 when we multiply by 4. And then plus, well, the sine of 2 pi over 3 is also root 3 over 2. This one doesn't have a coefficient. So we end up with pi minus 3 root 3 over 2. Now, I don't know what that is off the top of my head, but we can punch that into a calculator, which I have done right here. And my answer is 0.5435. And I wanted to compare that to the area of a circle whose radius is 1/2. And I noticed that 0.543 is significantly smaller than 0.785. But then I went ahead and graphed these and I compared, and I saw that, in fact, that circle does seem to be a lot bigger than that inner loop. So it seems like, at least with some graphical evidence here, that I can be convinced that this is the correct answer. It's definitely at least in the right ballpark. So I'm going to go ahead and call that correct. Hopefully it is.